When we are in the middle of dragging this object, the green highlight identifies the change that Sketch and Sketch makes to the number in order to match our mouse manipulation. If we go back into editing mode and then rerun the program, we get the same results that we had from direct manipulation. So far, we have defined 3 rectangles that, although similar, are defined and manipulated individually. Now let's turn this design into a more structured, repetitive pattern. In particular, let's rewrite our program so that it draws the same rectangle 3 times, spacing them evenly along the x-axis. One way to accomplish this is to use a common functional programming operation called map to apply a single drawing function to a list of arguments. In this case, we define a drawing function called drawI that takes an integer index I as an argument and draws the ith box. Notice how we use the same constants to specify the height, width, and y positions of all the boxes. To emphasize the purpose of these constants, we can define names for them. Now, when we rerun the program, we see that our boxes are evenly spaced. With this programmatic setup, it's easy to alter the number of boxes by adding additional index parameters. The number of boxes is a parameter of our design, so let's introduce a name for this number. Generally, the list of numbers between 0 and n-1 is common, so the little library provides a function called 02 to do just this. Now that we have reworked our program to capture the high-level intent of our design, let's see how we can directly manipulate the output. When we drag the right edge of the box, notice how all boxes are updated simultaneously. This is because the width of the box we manipulated is defined directly in terms of the w variable in the program. So, Sketch and Sketch figures that the only reasonable thing to do is to change the value of w in order to match our changes. This program update immediately affects the width of all of the boxes, which is precisely what we had set up our program to do. Similar updates are inferred when we directly manipulate other zones. We use the term simple update to refer to situations like this, where a single number in the program controls an attribute in the output. Simple updates are, well, simple for Sketch and Sketch to resolve. Matters are trickier when multiple values in the program affect an attribute in the output. Consider the x attributes of the boxes, all of which are computed by the expression x0 plus I times 7. Because the runtime value of this attribute for the first box is just equal to x0, dragging the first box is a simple update for Sketch and Sketch to resolve. By changing x0, all boxes are translated in unison. When dragging any box besides the first one, however, there are multiple numbers that factor into the computation of xi, namely x0 and 7. When hovering over the interior of these boxes, notice how these two numbers are highlighted. When there are multiple numbers that can be changed, we call this an ambiguous update, as opposed to the simple updates we saw earlier. There are several ways to deal with ambiguities in Sketch and Sketch. For now, we will mention just one. We can turn an ambiguous update into a simple one by annotating numbers in our program as frozen, which means that Sketch and Sketch should not, under any circumstances, modify it. Adding an exclamation point after a number freezes that number. For example, say that we are happy with the spacing between boxes, so we freeze the set constant. Now, even though set still affects the x position of all boxes except the first, Sketch and Sketch has only the option of changing the x0 value. So, when dragging any of the boxes, x0 is changed, and thus the entire group is translated. Alternatively, we can unfreeze set and freeze x0 instead. And now all boxes can be dragged and when we change set.
Okay, that is co-direct manipulation, and a short summary of how it works is that when it draws the image, it essentially keeps a trace of immutable values that it's created while executing the program. And when you drag things around, it then computes what those new values should be, and that propagates and tends to synthesize a small change to your program that produces your move. So those were a couple of examples of synthesizers. Which use code and which use specification. Rather, for storyboard programming, it did use examples, but it asked questions to make sure they were, quote, the right examples. So here's an example, a pure programmatic example, and if there are any Windows users in here, this is something that might already be running on your laptop. This is from Microsoft Research. And the creator of the first tool be shown here is my lab mate Rishabh Singh, who is also the creator of the storyboard programming tool.
To take programming to the masses, and what better application than data ready? I'm going to show you 2 demos of programming by examples. So consider this collection of email addresses in the first column. Suppose you want to extract the last name, as you see in the second column. If you would do this manually, it would be very cumbersome. A more principled way to do this would be to write an Excel macro. But if you're like one of those 99% of end users who do not know programming, you would be stuck. So in Excel 2013, you can use Flashfill to automate this task. So all that you have to do is to give an example and press Control E. So what the system does is it generalizes the example into a program and runs that program on the rest of the rows to automate this task. Now in general, it is too good to read the mind of the user from this one example, as this scenario illustrates. So here I have a bunch of medical billing codes, some of which have a right bracket at the end and some of which don't. Suppose your goal is to clean this data by adding a right bracket wherever it is missing. If you give one example, the system comes up with the simplest generalization, which is to write a right bracket everywhere. Maybe this is what you wanted and then you're done. But otherwise you would realize that row 6 to row 10 are incorrect. You can fix any one of these, which is like giving a second example to the tool, and the tool can better read your mind at that point. You can use this to extract relevant fields from big strings. All that you have to do is to give an example. You can use it to do sophisticated tasks like extract abbreviation. You can use dots. You may not use the spaces. You may print them in reverse order. In fact, the computer is actually generating a loopy program here. So this is my final slide. So what do you think I'm trying to do here? Extract the first letter, right? Here, maybe first 2 letters. First 3 letters. And what do you think I'm trying to do here? The first name, right? But let's say if I really wanted the first 4 letters, then I can give one more example and the system will do it for me. So the way the technology works is that it does not synthesize one program, but it synthesizes lots of programs that are consistent with the examples that the user has provided. And then it uses machine learning based ranking techniques to figure out which program is the intended one. And just to show you the power, this is my final example here. So I'm trying to extract the initials. And the system is intelligent enough to figure out that the small f actually comes from the lowercase version of the capital F here instead of the other small s in the first name. So now moving on to my second demo. No. So here is an assignment from a popular data science class at Brown University, where the students were asked to take this Wikipedia master file and convert it into structured format as you see on the right side. And the instructor gave them an initial script over which they wanted to build the solution. We believe that we can do this in a much better way. So here's the same file that I loaded in the technology called Flash Extract, which is shipping as part of PowerShell with the upcoming Windows release. So all that you have to do is to start giving examples of the data that you want to extract. So I've given them one example of the Super Bowl championship name, and the second example of the Super Bowl championship name, and the system extracts it for you. You can even look at the program that got generated. So the system says that in order to extract this blue label, you consider all the lines that begin with DTS, and then you look at the lines before, and extract the string between the last occurrence of left bracket and the last occurrence of bar in that line. Now you might want to extract other fields, so I change the color of the label, and I give examples for the second field, and in this case only one example suffices. I might even be interested in, let's say, extracting the winning score. Now if I do that, you see the system didn't get it right in the third report here. I can give one more example to fix it, but what if this mistake occurs somewhere deep down inside the document? We provide another powerful user interaction model based upon active learning, where the system is going to ask you, did you mean this or did you mean that, whenever it feels that things can be ambiguous. So in this case, it actually guesses this right, and you can say, yes, actually I went 16, so why don't you fix it? So if you want, you can go further, and maybe let's say, extract the name of the city, where this championship occurred, and so on. So you can load this file into Excel if you wanted to, or you can take this program that got synthesized and run it on other files in a similar format.
And much throughout the talk, we're actually going to be explaining how the first of those examples, how Flashfill works. So there we had 4 different synthesizers, which I all selected to fit the visual programming theme. And there's an entire scene more where those came from. So about 10 years ago, just my advisors worked in program synthesis. Today, I checked the proceedings of PLDI 2017, which is a really big programming languages research conference this year. Out of the 47 accepted papers, 8 of them were about synthesis. And there probably were a bunch more that were synthesis related. So, I could speak for hours, I could still not touch the breadth of synthesis applications available today. Right. So, step 2 of building a synthesizer is to define the search base. And typically that takes the form of some domain-specific language for the problem at hand. So this is most of the DSL for Flashfill. I'm leaving some parts out. Now, if you've done any work with compilers, you might have seen grammars or Java or Python, and these superficially look a little bit like this. I'll tell you that this is unlike any grammar you've ever seen. A property that most real languages have is compositionality. Like you have a function call, and it takes arguments, and those arguments can be expressions, which can be arithmetic, which themselves contain other function calls, and can go arbitrarily deep. This language here, you might notice, is not like that. That concatenate expression has to be at the very top. There are no others. There are no nested loops. Once you're inside a loop, then, let's see, actually, I lied. Okay. It's definitely the case. This is way more restricted than any language you've dealt with. So what does it have? It has a big old concatenate expression, concatenate a bunch of things together. We can have constant strings. It has a fancy thing where what I'll explain in the next slide, where you can search into a string with regular expressions and take a substring. You can take positions, you can do some basic arithmetic, but not arbitrary multiplication. All right. So yeah.
In the previous slide, you said the loops could not be inside a loop, right?
Okay.
Wouldn't the E kind of
Actually,
fall?
I lied.
Oh, sorry.
They can be. Yeah. What is? Yeah. What is? Yeah. There's still other restrictions on constitutionality, which is like you can't put a loop inside one of these substring expressions. The regular expressions here have to be constant. So I'll need it for the next slide. Just explain quickly. The way this fancy substring operator works is that you have a position says regular expression 1, regular expression 2, and k. What this means is find the kth instance where R1 matches the strings before the position and R2 matches the things afterwards. So we have a setup like that, and then the substring takes in everything in between. So if we set R1 and R2 prime to be the empty regular expression, what you're saying is, find the start position of this regular expression and the end position of this one, and take everything in between. And so, the big dilemma in designing these languages is the balance between expressivity and efficiency. It would be very nice, like, have an arbitrary Perl program as our matcher, but we would not be able to synthesize programs in that space because it's too complicated. Whereas what this language lets us do is still have very powerful string matching capability that can express. I think they're able to get literally all of the top 100 examples from an Excel help form. While it still has this so that an ordinary laptop can synthesize in a couple seconds. Just like an ordinary laptop like 6 years ago with this first being built. So an example of how to use this language. Here is the example of cleaning up some phone number data. Phone number formats, we want to put them all in the same format. And let's see, I'm using some match expressions which they glossed over. Essentially, it's looking. So this says it's going to look for some numbers, and then take those numbers, then put on a hyphen, put on some more numbers, hyphens, and more numbers. But there are many other programs that can do the same thing. Like this one just has a 425 hard-coded, which is not what we want. And so the overall setup for this problem is that it actually is going to synthesize an entire space of an exponentially number of programs. And it's going to do that for every single example individually. Then it's going to find the intersection of all of them, which still gives us a very large number of programs. It's like, but finding the hyphen this is, you could say like find the first hyphen, or you could say find the last character, or whatever. And there are a lot of ways of writing the number 10. And then at the end of all that, it's going to use machine learning because it has some knowledge of what programmer-written programs tend to look like. And from that, it can, about 80% of the time, figure out the program that you wanted with one example. Okay. So that is the search space. Now, we're down from, we have no idea what we're doing, to an exponentially large space of programs. Now, we just need to search this. There are two main ways of doing search. They are symbolic methods, constraint-based, or with dynamic programming, structured explicit search. Flashfill uses the latter. So, here's the transformation. I take someone's first name and add Mr. I did not write this example. It is not gender neutral. And there is an absolutely huge number of ways to do this. For this example, I could say take the first 3 letters, and that's the first name. Or it could say take everything up to the space. Or it could say look for the second capitalized letter and then go backwards by 2. So I don't know how many programs there are to do this, but it is over 10 to 100, I can tell you that much. It will not fit in your hard drive if you write them out all one by one. No, don't worry, we're not going to put them on your hard drive, we're going to put them in RAM. So here's how this works. The most important, every construct in that language has a synthesis procedure associated with it. The most important one is the concatenate one, which I'll explain now. So I can write down 8 different positions in this string. Now let's talk about all the programs that produce that M. That can be seen as the path from position 0 to position 1. And I don't know, say I have 10,000 programs do that. Now I have 10,000 possibilities there. And I can have another 10,000 that produce an RB, and so on. And any concatenation of any of these programs that produces one string of letters is a valid program. However, because I've used this DAG structure, this DAG encodes every single path. So I can write down exponentially many programs in a small amount of space. And it works similarly for all the other constructs of this language. So here it is for the substring. So I want to talk about every substring expression which can produce 145.67 from that string. Well, I can have a bunch of ways of writing down the left endpoints. Say look for like the thing after $sign, or the thing before a decimal, and or whatnot. I can do similarly for all the things on the right. There are quadratically many ways to combine them, but I just write them like this, and it represents all possible ways. Doing this, we could now represent all 10 to 100 operating programs in a very small amount of space. And the next steps of this, which I won't get into, are you have this data structure, you can compute intersections with a data structure, and then there's a very fancy way to, well, I can't run a machine learning classifier on all 10 to 100 examples. So there's a very fancy way of doing an upper bounding search to rule out large parts of the search space at once. All right, I'm gonna pause here for questions.
The compactness is something that strikes me in relationship to trying to learn how genetic coding of structures might work. Now, another analogy that I've thought of before is again the Mandelbrot set. All of those patterns complexity growing out of a simple quadratic equation. So here you have it's a very compact way to write huge numbers of variations.
Yes. Any other?
Maybe, was that a comment or a?
That was a comment.
Okay, that was.
Of the person.
Yeah, I was thinking like, don't get rid of questions there. Right, of course.
Okay, I think I might have missed this, or maybe I'm misunderstanding the text, but why is the search space not infinitely large?
Ah. Okay. Let's see. So there's a very important property of this language that we designed, which is so okay, ignore this thing. Actually, not quite sure how to handle it. Let's see. Actually, no. I believe the way they handle this is that it won't be synthesized unless it runs at least 2 iterations. So the really big thing is there's no delete operator, and you're limited to taking substrings of the original string and piecing them together in some way to work instance. So absolutely. So not only is the depth of expressions kind of limited because of that, but also absolutely everything here will produce a new character. So we very carefully designed language to make it tractable. Yes.
You actually start out with an exhaustive set of all the correct programs.
Yes.
Okay.
You synthesize, you write down every single program that will take a single input to its corresponding output. And you saw it running in real time.
Well, you don't need to find all the programs, you just need to find one, but when you have many examples, you need to fit all the rest of the data, right? So that's where we get to pruning on.
Yeah, so the big thing is the way this works, it actually is, it is fairly efficient to find all of them. And really the induction procedure requires it in that, so like we found all the things that produce ROB, and now we're looking for the things that produce Mr. Rob. Well, the one we're looking for might involve one of those. And the second thing is that for the ranking, for the ranking, you let it could be any of those, but you write them all down compactly, and then you can apply the ranking procedure in a second pass.
Hello, Bill now. TH1000 for.
Sorry. Artificial intelligence.
Yeah, and I mentioned there's a machine learning ranking procedure. That is the only AI that's anywhere in this talk. This is not AI. Okay, so now I'm going to talk about the other big kind of search, which is constraint-based methods. And for flash fill, they built all their own infrastructure. They wrote some really fast C++ to do it. For constraint-based search, you can actually use an off-the-shelf solver and write your own synthesizer very fast. So here's my 10-minute guide to how to build your own synthesizer using the power of this thing called Z3. Z3 is an S&T solver. And actually, out of curiosity, has anyone here ever heard the term S&T solver before? Okay, a couple of you. Yeah, these things are really damn useful, and not many people know about them. So, S&T is satisfiability modular theories. So if you took a theory computation class, you might have learned about the Boolean satisfiability problem and how it was really hard to solve a bunch of problems. Well, they lied to you because it's actually really easy. And what it does is you give it a big logical formula, a bunch of ands and ors, and it says, here's a way to make it true. The modular theories in S&T means now we have Boolean formulas with the theory of arithmetic and the theory of arrays, which means now instead of having formulas containing like ones and zeros and ands and ors, I now have them containing arbitrary integers and less than and plus. And all these things are useful for actually talking about programs which contain things like arithmetic and arrays. So here's an example SMT solver in action. You can input in a number of ways. It has Python bindings, it has camel bindings. It also has its own language, which looks like Lisp, for writing down logical formulas. So here's some dumb example. We just said, A is greater than 10, the other thing is less than 100, give these commands, and it gives you a satisfying model. And you can encode all kinds of verification and synthesis problems into an SMT solver, ask for a model, and just read out an answer. And that is how we're going to use it now. So we are going to use it to fix a buggy program for us. So here I have an example program which solves the triangle classification problem. I give it 3 integers, and a greater than b, a greater than equals b greater than equals c, which represent the sides of a triangle. And it's going to tell me whether it is acute, obtuse, right, equilateral, or isosceles. Has anyone spotted the bug in this program yet? Alright, I'll have Z3 take a stab at it. So here's how we ask this question to the SMT solver. First, I just happen to have chosen an example which is very easy to encode in Z3 because it contains no loops. Things get harder when you have loops, and I'm not talking about that. So this looks like it's still a function. Actually, because it's Z3, this is now a logical formula. And this means I can write things like, give me an x, y, an A, B, and C, which are a right triangle, and we'll just run this program backwards and solve it. Why? Because it's all boiled down to a bunch of constraints. Constraints go both ways. And now I'm going to, to write down a precondition, triangle inequality. And now I'm going to assert that the output of the classifier on whatever A, B, and C I come up with will satisfy some specification. And I can write the specification however I want. I can write it as a correct version of the program, like maybe this is a homework assignment. Or I can write a partial spec. It's like, here's a machine that generates right triangles, make sure it works with anything that generates. Do this a number of ways. And if I run this, it will then give me an example where this fails, which is A equals 2, B equals 2, and C equals 1, which does in fact trigger the bug, and it will erroneously be recorded as not isosceles. So now we've encoded this program into Z3. We've managed to ask it about the bug. Now here's how we synthesize a repair. Yeah, we're going to do this using synthesis by sketching. That is, I'm going to find some little language of possible expressions which can be the fix. Here I said, let's see. Yeah, so here I said it is some ands and ors of A, B, and C which is compared to each other. So that's my base language. And now, what we're going to do is we're going to replace the buggy expression and say, give me anything from this language, such that the entire program is correct. So now we need to ask it how to give us anything from that language. And So, let's see. So basically the problem of making a bunch of choices from this language over and over. So it's either and or or, that's a 0 or 1. It's either A, B, or C, that's a 0, 1, or 2. So we have a bunch of these integer or whole variables, which are going to encode that. So our expression looks something like this. We say, if something like if h0 is 0, then put an and here, else put an or here. And now when we choose values for the whole variables, you essentially have chosen an expression from this language. So let's see, keep going through this, and yes, yeah. So we put in our whole. We can now say, please classify these examples correctly. And now it is going to think very hard. It's going to look for values of those wholes. It's going to look for an expression to put to replace the buggy formula, which is going to make all these examples work. And so we do that, and it gives us the correct formula: A equals B or B equals C. All right. So that was a 10-minute guide to building your own synthesizer. And if you go to riseforfun.com, you can find all kinds of tools from Microsoft Research, including Z3, which we were just talking about. You can look at the Synthesis Summer School, which they have here, and learn a lot of the basics. And I'd say my one contribution to this talk, that programrepair.org, which is a portal site for things that automatically fix bugs and other programs. I used to own that URL. I sold it to the current owner. It's one contribution to this talk. Synthesis is still a fairly burgeoning field, so there's not a really great collection of resources all in one place. You can just go to learn it. But nonetheless, this stuff is eminently hackable. It's like, if you can learn how to do deep learning and make your own handwriting recognizer or something, then you can learn to do synthesis and make your own program repair tool or visual programming tool, or I don't know. So I just came here today bring some technology. Now the future is in your hands. Thank you for coming. Questions?
Have you worked with any tools that represent code as a graph database?
That represent code in a graph database. Can I ask why you're asking that?
For just navigating code.
Oh, okay. Yeah. I was wondering because, have you ever heard the term graph before? It's a very fancy word for abstract syntactry. Don't use it. Okay. So the question is, a tool that represents code in a graph database for navigating links. No, I have not. However, I can tell you that Kite uses a graph database to represent objects on GitHub so they can do their statistical analysis.
So, do you see this being used more, or is going to be part of our Excel tools or editors, or how is it going to be used, do you think, in some future exercise? These are neat examples, but...
Yeah, so my hope is that we'll actually be able to get a lot of these things into IDEs, into your standard programmer's toolbox, to a lot of tricky things for you. And to a small extent, it already is. I know I can definitely name a bunch of synthesis tools or R Eclipse plugins that might help you with piece of Java that actually do have users. And we discussed this problem earlier today. A big problem in the developer tools industry is that it's really hard to develop this pay for things. And as long as it's true, no one will build something that's worth buying. but maybe you'll be the one.
Do we have any more questions on this specific topic? Go ahead.
Yeah, you'll forgive us because we got stuck in traffic and we're here late. But can you tell us a little bit about what you do with program repair? Sorry to repeat for anybody else, but
Alex, right?
yeah.
The answer is currently nothing. I used to have a company which tried to build things for repair tools. It's long dead. And I can tell you, if you go to programrepair.org, the stuff that's being done nowadays is way more advanced than what I was doing 4 years ago. Yeah, so I know in the abstracts of this talk I mentioned this tool called Angelics, where they actually managed to synthesize a repair to the heartbeat vulnerability. Boris?
Can I ask about another, so like practical application? So I write Scala at work and we have a lot of bugs. And we also have a lot of unit tests.
Mm-hmm.
So how far away are we from a world where when there's a test failing, I can just press a fix and the program will rewrite itself to satisfy that unit test and be meaningful?
Yeah, so okay. Well, if you happen to be an academic who already has one of these tools installed in your code base, the answer is like maybe 2 years. So that's the question. Like, it could be 3 years, it could be 20, it could be 1 year, it could be 20. And we have mostly technology. The question is, do we have commercial power? Agree?
My question is the opposite of that. If you had some code that you're working on, what about the task of generating the tests from that as the initial step?
There's already so that is, you say it like generating tests, like one small thing. I mean,
well, generative tests in a very bounded,
it's like that's a huge spectrum of things to describe. Automated test generation has been an area of research for the past while. I can tell you one of the biggest results in this was about 10 years ago. This tool from Stanford called PLE. It's symbolic execution. You know the Linux core utils, programs like ls and pwd. Some of the most heavily tested code on the planet, their completely automated system was able to find bugs in it and generate higher coverage tests than 20 years of manually constructed test suite. But I'll tell you,
like a program equivalent of fuzzing, basically. In terms of automating different inputs and outputs.
Yes, it serves the same role as fuzzing, but uses symbolic constraint solving instead of random test generation. And then they're all, and that area's been pretty active. So there are all kinds of things combined to do.
Have you seen Clojure spec? You might want to look into that. So for Clojure, that's a really popular test.
Right.
And I think it's actually interesting because Clojure is not a statically typed language, which I think makes this thing harder than it should be.
You had a question, Mike?
I did have a question. You said C3 has trouble synthesizing loops. Does it do it at all?
Okay. It's not that Z3 has trouble synthesizing loops. So first, with Z3, when you write expressions in Z3, you must have a fixed number of variables. Loops typically have they're unbounded or entering things. So what you need is you need to have a way of encoding your loop into a finite language like Z3. And there are two ways of doing that. One is bounded synthesis, bounded verification, where you say, I'm assuming this loop runs at most 20 times, and then you unroll it 20 times. The other way is that you search for some kind of invariant. And that's, people have done that with different levels of success. There have been pretty impressive examples of people doing that, but it is our problem. Basically, all the questions about how to handle loops, Z3 is a fairly low-level solver. It is, it is the infrastructure in which a lot of this is built on. Loops is handled at a higher level.
Are slides available?
They will, yeah. I finished these like 10 minutes before the talk.
Alright.
So have you, forgive me if I missed this or talked about it, but have you done anything with interacting with a conversational style about code? Like, so there's the messages that tell you what's wrong with code, which are notoriously unhelpful, and they'll tell you.
To a very limited extent, yes. So by conversational, you mean with queries or with actual natural language?
Well, there's kind of two elements to conversational interfaces that are becoming popular right now. One is the actual language itself, which may or may not actually let you make input in natural language. It often has buttons, but it's also the interrogative style. So an error message in programming compilers will tell me something like null reference exception, or unexpected curly breaks or whatever, right? And what it actually means is that there's some other problem, but I have to kind of piece through it, and then the message just disappears. But it doesn't let me say, for instance, like let's say it's a null reference exception. I'm trying to think of an example, but like it can't talk me through possible solutions to the problem. So ReSharper and a couple of other tools have had things. I don't remember like too clearly because I haven't used them very much, but they'll say things like this code is never used, like this variable is an unused variable or something like that. Those types of little messages have a right-click menu where you resolve the conflict, or you resolve the issue with some kind of separate choices that are provided to you, where it's kind of like, do you want to do this or do you want to do this? And you don't have to like talk to it verbally, but it's presenting you something much more rich than an error message.
Yeah, so I'll mention a few things which might kind of fit what you're looking for. So first, I'll preface this by saying, one general thing that we are very bad at in programming languages is having the machines come up with their own abstractions. We can have it do all kinds of fancy reasoning at a very low level, and we can have it reason with fixed abstractions. But learning new abstractions and actually talk about your code in the way that you think about it is still out of reach for us. So here are things we can do. One of the videos I showed at the beginning for synthesizing data structures with whiteboards, he was talking to the computer, literally with voice, but it's a fairly fixed dialogue system. The Programmer's Apprentice has some similar stuff. You can say, this video where the creator is asking it, so, will this output stream be able to keep up with, with the camera inputs? Like, no.
So you'd have to go to as a race condition or something.
Not a race condition, but it's
called the Programmer's Apprentice?
The Programmer's Apprentice.
That sounds really interesting.
Yeah, they're also 30 years old. Very, very important. And probably the thing that's most helpful for you is not natural language. The Y line by Andy Coe from the University of Washington. Basically, you can have a little graphics program, like right-click on it and say things like, why isn't this line blue? And then it will try to trace backwards and figure out all the things that could have made that line blue and tell you why they didn't happen.
Not enough coolants, some people would say. Maybe.
Right.
We should wrap it up here,
Yeah.
but everyone is welcome to stay in the back and we can have a discussion
I'm
there.
sticking around for probably another hour or so. So, if you have any questions, I might know the answer.
Yeah, we do.